Okay, so we are nearing the light at the end of the tunnel, okay, for the fall semester, which is nice. Let's see. Today we are finishing up integrals in electric circuits. So we'll post a homework on that, right, due next week. And so end of week 12, right? And so looking here then, what do you have going on for next week? Some more lab, right? And then after Thanksgiving, you'll have the MATLAB final coming up, right, during regular lab meeting. Your lab TAs will talk more about that operation. Okay, but it looks like you still have some regularly scheduled lab coming up next week. Okay, and yeah, and so let's see. Next week, differential equations. Okay, so that's it. That's the last topic, right? We'll do differential equations intro and starting some mechanical systems next week. Finishing up mechanical systems before we head off to Thanksgiving, right? And then finish up with diff EQs and electrical systems week 15. Okay, so there's where we are. Questions about the big picture before we move forward? So just some words of advice for first year students in particular. Do some planning right now on your time usage towards the end of the term. Right? I know how this works. If you got some gen ed classes, you could have papers due at the end of the term. You got finals week coming up where you'll have finals stacked up. In here, the final exam, we try and do this for a soft landing for you guys. We use the unscheduled block on the Thursday of finals week. So you've got the whole finals week there where we can also get review sessions and office hours and all that kind of stuff in. And we don't have any expected conflicts with that because it's the unscheduled block during exam week. So nobody else will have a class conflict. So we'll fill up 109 Ullman pretty well for the final. But really, we're talking about December 12, right? So I mean, we're looking at, I guess it's 4 weeks, right? 4 weeks from today. So it's a chunk of time. So you can really make sure, that break in Thanksgiving where you've got that little bit extra time off, you can kind of rejuvenate, but then even have that weekend there to really get moving ahead to close out the term. Okay, so plan ahead accordingly based on where you are in this class and what you think you need to do. As I said, anything is possible on the final exam. All right, whatever happened to you on the first 2 exams, I've seen it done. I've seen 2 back-to-back low C grades turn into 100% on the final. Okay, it can happen. I've also seen back-to-back high grades turn into like a C on the final. Okay, that can happen too. You don't want that to happen. So just plan accordingly and be ready to go. Okay. So finishing up electric circuits, integrals in electric circuits. I think we left off where we were doing current voltage in an inductor and actually doing the integral to get the equation of the line, just to make the point that we could do that. Now I want to move on and take a look at a capacitor, more of these sketching kind of problems. Okay, and so here's an example. This is going to be current and voltage, okay, in a capacitor. Okay, and what we're going to do is go back and revisit, again, a similar problem that we had looked at with derivatives, but again, now we're doing integrals. So can we use the areas under the curve, not just the concept of slope? Okay, so what we'll have is effectively here is this is going to be a current source. Okay, so there's going to be a current here, I of t. Okay, and what we would like ultimately is to sketch the voltage across the capacitor. Okay, and so I'm looking at the little hand sketch in the notes. It's a little bit backwards here. It's an I of t here, and then ultimately we'll want the plus or minus V of t across the capacitor. Okay, and the capacitor over here is C, and we're going to use 20 microfarads for that capacitor. Okay, so here's what we've got. Back from when we looked at derivatives, okay, we did a plot over here of I of t, which is measured in amps. Okay, and then, just to keep your wits about you, realistic numbers here, we've got the t measured in milliseconds, so you have to keep that straight. Okay, and here's what we did. Every 1 second, we changed the current source. Okay, so we went out here for 5 total seconds. Okay, and essentially we're moving the current around between positive 4 and negative 4 in the following way. Okay, so we'll have 2, 4, and then 0, -2, -4. So for the first 1 second, okay, we're going to be at 4 amps. Okay, and then we're going to drop down to -2 amps, okay, for the next second. Okay, and then we will bounce up to +2 amps and hold it there for 2 seconds. Okay, and then we're going to bounce it all the way down to -4 amps. Okay, and we will hold that there just for 1 second. Okay, and so here's what it looks like. All right, and so again, on the x-axis, these are single-digit milliseconds, not seconds. Okay, so what we would like to do is, given the current voltage relationship, I of t is equal to C dV dt, okay, which means, right, that the voltage is then the antiderivative. If I divide both sides by C, I'll get 1 over C, right, times the antiderivative, the integral of I of t dt. Okay, and so knowing that information, what we want to do is sketch V of t, okay, if the capacitor is initially discharged. So V of 0 equals 0. Okay, so we've got a starting point at 0, and I want to use the idea now of integrals, okay, to go from this plot for current to a separate plot for voltage. Questions on the plan before we move forward? All right, so here's the idea. Different current in every interval, so I ought to be able to look at this one interval at a time. So for example, the first interval, 0 less than or equal to t less than or equal to 1, okay, and of course this is milliseconds. Okay, you want to start by writing down what it is that you know. So according to the given information, right, this is the I of t here. Okay, and just to be clear, right, this plot is the I of t. This plus or minus V is the output across the capacitor that we want to find. What is the current for the first millisecond? 4. All right, and so the point again is it's not just 4 at one point in time. It is 4 for all points in time in between 0 and 1. So I of t is equal to 4 that entire time, and so what kind of function is that? It's a what? It's a constant. All right, this is a constant function. Okay, and so the point being then, if the current is a constant, okay, and the voltage, right, is 1 over C times the antiderivative of the current, then what kind of function will I get if I integrate a constant? I will get now a line, right? So this is a linear function. So I know I'm sketching a line. Okay, so again, flashback to when we just had derivatives, right? Same idea, and then we thought, well, I can use slopes, right, in order to sketch lines, and voila. Here, I don't need to use the idea of slope, because if I know it's a line, and I've got a starting point, V of 0 equals 0, okay, then if I could just find the endpoint, then a straight line means just connect the dots, right? So what the integral also allows you to do, all right, as we saw last time for the inductors, okay, is we can say that, well, the change in the voltage, right, which would be V1 minus V0, okay, between those 2 points in time, right, is equal to this guy over here, 1 over C, right, the integral from 0 to 1, that's milliseconds, right, of I of t dt. Okay, and maybe to be crystal clear, okay, when you're working with this and you know you're going to have to put C in here in microfarads, and you know these limits are milliseconds, you could follow my golden rule, which says when in doubt, just put everything in base numbers. So even at this point, why not just do this? 0.001 like that, so we're clear. Okay. All right, so let's go ahead and put the numbers in, see what we get. So V1 minus V0, okay, and so V1, what's V0 equal to? That's 0, right? That's this guy right here, V0. Okay, it's equal to 1 over C. The C is 20 microfarads, So a micro means what? 10 minus 6. So it's 1 over 20, right? Capital E minus 6 is the way I'll write that. Okay, we could write it as times 10 minus 6. Okay, and by the way, this is what number? It's the same problem from derivatives. I remember the answer, right? You do that in your head. 1 over 20 E minus 6 is what? I get a 5, right? And then I got an E minus 6, right? But this is a 20. Anybody? Can you use your calculator? You know, I ask you this stuff all the time because even though we have calculators, right, as engineers, right, you guys got to get more comfortable with just the numbers, right? Always thinking about the number. Does the number make sense to me? Can I do a sanity check on the number? Okay, so, you know, get used to using your technology. You're always going to use it, but don't give up on your ability to look at that and say, yeah, that's 50,000. Okay? All right, so I'll have 50,000 in front. All right, and let's see. Integral of I of t dt. So I got a couple choices, right? I could put in what I of t is, which is just a number, and do the integral. Or I could use the idea that, wait a minute, that's a definite integral. Definite integral is an area on a curve, right? So this guy right here is the integral from 0 to 0.001 of I of t dt, right? The area of that block. So help me out. What's the area of that block? The height is 4, right? The base is what? 0.001 is the base, right? And the height is 4. Okay, so again, if you do it like that, everything's in base units, right? So that means the voltage you get as an answer will be what? Base units, which is volts. Okay, so this is the danger again when you get these mixed unit problems, like this is amps, but this is milliseconds, right? If you're not careful, you could screw up your orders of magnitude. Okay, so when in doubt, when the numbers go in, base units for everything will take care of itself. Somebody want to crank that out for me? What do we get? Yeah, 200. Okay, and so this is then going to be 200 volts. Okay, and then at this point you come back and do a sanity check, right? This is a circuit where I'm pumping through current in single-digit amps. And so I got a 20 microfarad capacitor, which is a typical kind of number. Okay, and then the output of that is voltage in hundreds of volts. Okay, so these are the same kind of numbers you think of in household current, right? You got 110 or 220 for your dryer, and the amps coming through there are single-digit amps typically, right? Yes? Okay. All right, good. So 200. So that's it, right? It's a line, and it ends at 200. So we'll leave this maybe here for some more calculation. We'll plot it over here. And so we want to plot the voltage V of t. Okay, and so same axis over here. We're going to go out for 5 seconds long. All right, so this is t out here, sorry, milliseconds long. Okay, and so in milliseconds, this is 0, 1, 2, 3, 4, 5. Okay, again, it's another hint for you. If this really bothers you, right, if you screwed this up on the second exam because there was milliseconds and things, nothing's stopping you from calling this seconds and writing 001, 002, 003. Right? I mean, that's exactly what this means if I label it in milliseconds. Okay? So I've got the x-axis. And then the y-axis, I know I'm going to be up to a couple hundred volts. So we should probably put some tick marks here in the hundreds of volts. Okay, so we'll put a few of them on here. So I got 100, 200, 300, 400, like that. Okay, and again, what we're plotting here is V of t, units of volts. So after 1 second, I got a straight line, got a starting point at 0, got an ending point at 1. Only one way to draw it, like that. Okay. By the way, what's the slope of that line? So the rise is 200, and the run over here is how much? Is it 1? 001. So the slope is 200,000. Does that make sense? Well, dV dt, the slope, right? We write it here. This is a double check. dv dt is the slope. It's supposed to be 1 over the c times the current I of t, right? So 1 over c is 50,000. Yes? Right here. So this is 50,000. And I of t is how much? 4. 50,000 times 4 is what? 200,000. Okay? Again, that's the fundamental theorem of calculus right there. Okay? The fact that I use the area to sketch this plot, but when I go and look at the result, I get a slope that I get from a derivative relationship. Right? That's the connection between derivatives and integrals. Okay, so there it is. So we double check that. It all makes sense. Great. We're moving on. Questions? So similar idea now. Okay, and frankly, once you do this detailed analysis for one interval, you can almost just look at each one of these and see what it's going to do. Right? I mean, it's going to be lines. You can look at the numbers and scale it and get pretty close. But we're in good shape time-wise, so let's just go ahead and crank these out one interval at a time. So if I now go to the next one, which is 1 less than or equal to t less than or equal to 2 milliseconds for the interval, then that's this range right here. So I of t is equal to what? I of t is -2. Okay, and what kind of function is -2? That is a constant. Okay, and so if that is true, okay, then the voltage, V of t, is going to be what? 1 over c times the antiderivative of I of t dt. Okay, and so this is going to be a line, linear. Okay, and so do I know a starting point at t equals 1 millisecond? Yeah, it's where I left off, right? This is my starting point. So once again, if I know it's going to be a line, and I know where I left off, then all I need is the end point, and I can connect the dots. The integral is what gives me the end point. All right, so now we'll go ahead and say also, all right, this is the indefinite integral. The definite integral says that v2 minus v1 is going to be 1 over c, all right, times the integral from 0.001 to 0.002. Right, of I of t dt. Okay, and so now we can put the numbers in. Right, v2 minus v1 is how much? What's v1? I got 200 on the plot, right? So v2 minus 200 is 1 over c. That's 1 over 20, e minus 6, 50,000. And then this integral right here, okay, is now going to be the area, right, of this box. Okay, and so what's the area of the box? Integral 0.001 to 0.002 I of t dt. I need the base times the height. The base is how much? I got 1 millisecond, right, for the base. So base units, 001 is the width of the box. What's the height of the box? -2. Okay, so there's the number. And you can see actually by looking at these numbers, this will be half as much, right, but with a negative sign. So you run this number and you're going to get -100. So apparently V2 is equal to 200 minus 100, which is 100 volts. Okay, and so that's it. I got over here to 200. At the end of the time, I'm going to be over here at 100, and bam, there I am. Questions? Pretty straightforward. All right, so we got two more regions here. So if I look at the next one, I've got now not just 1 second, though. I got milliseconds. I've got 2 milliseconds on the axis. Okay, so 2 less than or equal to t less than or equal to 4 milliseconds. Okay, in this range, I of t is equal to how much? I of t is equal to 2. What kind of function is that? It's a constant, right? You start to see the pattern here. This gets a little redundant. Okay, so this is constant. So that means that v of t, which is 1 over c times the antiderivative of I of t, right, is going to be what? Linear. Okay, and do I know a starting point? Yeah. I know a starting point. It's right where I left off. So I know v2. Okay, and so what I can also say from the areas is that v4 minus v2, right, is equal to 1 over the c, which is 20e minus 6, right, or 50,000, okay, times the integral. And now I'm going to go from 0.002 to 0.004, okay, of I of t dt. Okay, and so you plug the numbers here. v4 minus v2. v2 equals how much? Yeah, v2 is 100 on the plot. And I've got the 1 over 20e minus 6 here. And then I need the area of this box. So now I come here and I say, well, the area of this box right here is the integral from 002 to 004 of I of t dt. So the base of that box is how much? Yeah, it's 2 milliseconds. So 0.002 is the width of the box, right? Right here. And the height of the box is how much? I got 2 amps for the height of the box. So that's it, right? I got 2 times 2 divided by 20. I'm going to be back with another 2. This looks like another 200, right? So I get 200 volts. Okay, so apparently V4 is going to be 100 plus 200, which equals 300 volts. Okay, so starting at 100, going up 200 more, doing it over here at 4 seconds. And there you go. All right, and then finally, look at this point. I would even argue, let's not do the analysis for the last one. Okay? What are we doing here? We're doing areas of boxes that are giving us hundreds of volts. So take a look at these boxes, right? This one's, right, 2 tick marks wide, 1 tick mark tall. All right, so what's the, how do the areas of these boxes compare to each other? How about the last box and the first box? It's the same, but negative, right? How many volts did I get here? Yeah, right, so if the first one was 200 volts, doesn't this last one give me 200 volts down? Okay, so you getting this, right? So you can show the redundant analysis if you really want to be anal, but if you've got this right, it's the same box going the other way, right? So I know when I'm done, I'm going to be 200 back down. Okay, it's going to get me back to 100, bam, like that. So the goal of this might be, for example, to figure out what the maximum voltage is. What is it? Yeah, so I can come over here and label this, right? Vmax is equal to 300 volts. That's the kind of thing we might ask you, right, on the final. Plot the curve, give me the maximum voltage. Make sense? All right, very good. So finally, the last one we've got for integrals and circuits, okay, is a good way to wrap it up, because it's one where I think to really get it right, I think you'd have to have some derivatives and some integrals. Okay, and I want to point out again that you will be doing sketching like this on the final. Okay, and the problems we cook up will be designed so that you're just supposed to use calculus. Okay, use some derivatives, use some integrals, whatever. Unlikely, actually, that you'll be able to get the numbers right without the integrals. Okay, so the slopes tell you a lot about the function. Is it increasing or decreasing? Is it linear? Is it quadratic? Those kind of things. But the slopes themselves, right, unless it's a line and you can figure out the endpoint from the line, for anything that's not a line, the slope itself, not that helpful for the actual number, right? So you need the areas under the curve in order to get the numbers. So you put these two things together, derivatives and integrals, and all you need are initial conditions for a problem and a sketch. And then you can use combinations of slopes and areas to do what you need to do. Okay, so here's an example again with a capacitor that'll show how this is useful. Okay, so this one, again, will have a current source. Okay, and except what we're going to use for the current source this time is going to be a sawtooth wave. So here's I of t. Okay, and this is going to be the capacitor C. Now this one's interesting. We're going to use farads, 0.5 farads, not microfarads. Okay, so what we end up having here is a plot that is in time of seconds, not milliseconds. So I'll have I of t over here in amps, okay, and we're going to do this over single-digit kind of seconds. Okay, and what we're going to do is a sawtooth curve that essentially just goes between plus or minus 2. So here's 0, here's plus 2, here's minus 2. Okay, and so this will define the amplitude of the sawtooth function. And we're going to do this over a period of 6 seconds. Okay, like so. Right, we'll start negative and then we'll go up to positive. Right, like that over a period of 2 seconds. So, and then it will drop straight down, and we're just going to do it again for each one of these cycles. Drop straight down, and then the last cycle like this, okay, and then drop straight down. Okay, so there it is, and so the numbers on here, this is 1 second, 2 second, 3 second, 4 second, 5, and then finally 6. At the end. Okay. All right, so knowing what we know, okay, which is this business right here, okay, I want to sketch v of t again if v of 0 equals 0. So the rest of this problem statement is still the same, okay, but now we've got a different input function. Questions on this before we move forward? General rule of thumb, all right, when you're doing these sketching problems, if the input function is a bunch of constants, then the slopes themselves oftentimes can help give you numbers. Okay? But if the input function is beyond a constant like this, then you probably have to start thinking about areas and things to get some numbers. Okay? All right, so first of all, what kind of function is a sawtooth curve like this? It's piecewise defined, that's true. What else can you say about it? Periodic. Periodic's always good when you're being asked to analyze something, right, or plot something, because it means that to really understand it, you've got to consider exactly how much of it. One what? One cycle, one period. So if I can get this thing figured out for one cycle, and as long as I'm back to where I started, well then that's it, right? I just repeat the result. So periodic input in, periodic output out, I'll be in good shape if I can understand one cycle. So great. This problem's broken all the way down to, can we figure this out for 2 seconds, right? And then can we just repeat it for the next 2 periods shown here? So understanding that, I want to think about it for the first 2 seconds. Okay, are there any places of interest within that first 2 seconds that you think you might want to know? Okay, and I want you to think about this one, using derivatives and integrals, right? This is like the cap on the sketching problems here. Here's what I know. I know that I of t tells me about a slope of v, right? I know that v is the antiderivative of I, and if I put limits on this, I can get numbers for v, right, based on areas under this curve. Right? That's the tools I have. So the slope piece, any points of interest in the first 2 seconds here relative to the slope? All right, so anytime I got a function that crosses the axis when I'm doing sketching, that immediately needs to trigger a response here, right? So this could be an intermediate result. You could have on a final, it could be a position velocity acceleration problem. You could sketch velocity, right, given an acceleration, and that could cross the axis. Well, if that crosses the axis, you want to take a look at that point and say, well, that probably matters when I sketch position because it's a flat spot, right? So always looking for flat spots to help do the sketching. So yeah, I'm going to want a number for voltage right here. Okay, so this kind of suggests that even though this is the same function, right, for the whole first 2 seconds, you know, and I guess maybe we could even approach it that way. We're going to have to look at least at a subset of that interval if we want to get this value, because it crosses the axis there. Okay, so we can think about it like the whole interval. 0 less than or equal to t less than or equal to 2. And we can make some general statements first about the type of function. So first of all, I of t, right, is what kind of function between 0 and 2? It's a linear function. Okay? And so I can use my knowledge of derivatives and or integrals, knowing I is the derivative of v, and that derivative is a line, okay? Or knowing that v of t, right, is 1 over c times the integral of I of t dt. If I integrate a linear function, I get what? Yeah, so we know we're dealing with a parabola here. Okay, so this is quadratic. So I'm going to have to do a parabola. Okay? Now, do I know what kind of parabola it is? What does that even mean? What kind of parabola? Yeah, concave up or concave down. There's 2 ways you can do parabolas, right? I mean, is it one of these or is it one of those? Okay? And so before I do any numbers, can I understand what it is I'm trying to sketch here based on the slopes? Okay? And so back up the card a minute here. Can we be more specific about the kind of line that we have? How would you describe this line? It's increasing. So it's linear and it's increasing. So if I, which is the derivative of v, is increasing, what does it literally mean about the plot of v, which we know to be a quadratic? So its derivative is a line, and it's increasing. So the derivative represents what on the v curve? It's the slope of the tangent line, right? It's the slope of the v curve. So the statement is that the slope of the v curve is increasing. Right? So, you know, increasing meaning going from left to right, right? So is it one of these or is it one of these? Which one of these has an increasing slope? The right one? The left one? Right? The slope is this guy, right? Here's the slope over here. This one, the slope is negative, then the slope is 0, then the slope is positive. This one, the slope is positive, then the slope is 0, then the slope is negative. Which one of these two represents an increasing slope? It's the left one, right? Now, position velocity acceleration, I've got some actual advantage because I actually have a second derivative plot right there, right? I can look at acceleration, 2 derivatives of x, and that's the concavity right there. Okay, but this is the same argument. If I thought of, you know, how is the slope changing? Well, the slope is changing on the v curve. It starts with a negative slope. It ends up at a 0 slope. Then it has a positive slope. So again, I'm going to be plotting upside down, well, sorry, right side up parabolas like this, okay, where apparently starting at 0, below the axis, right? Because the initial condition is v of 0 is 0. So you see what I'm doing here? I got no numbers on the board, right? It's trying to qualitatively understand what I'm doing before I even crank out any calculation is a smart thing to do. Understand what it is you're trying to sketch and then figure out what you need, right? So if I'm going to sketch these parabolas, then what I'm going to need is probably this point in the middle, right, the flat spot. And so great. So it's a quadratic with, I'll write it right here, with increasing slope. Okay? And of course that means concave up. So how's this? I'll just draw it. It's happy. Okay? Quadratic with increasing slope. It's going to be one of those. All right, so if that's true, then again what I want is I want this guy right here. So in order to get the number now at 1 second, okay, because that's where the slope is not necessarily helping me here, okay, I can get the number by saying V1 minus V0, the change in the voltage over this first half, right, because I want the number here, okay, is going to be 1 over c times the integral, and these are whole seconds here, so 0 to 1 of I of t dt. So if we put the numbers in, we ought to be able to get the value of V1. Okay? So let's try that. So V1 minus V0, how much is V0? V0 is nothing. Okay, and then I got a 1 over c, that was given. 1 over 0.5, so that's just going to be 2. 1 over 0.5. And now I've got this integral, which I could put the equation of the line for I of t. I could do a y equals mx plus b, right? I could plug that in. I could do the integral. I could get the quadratic. Or I can say, wait a minute, isn't this just a triangle? Okay, so this guy right here, this triangle, is the integral from 0 to 1 of I of t dt. Right? And so this requires that I know how to do the area of a triangle by geometry. Half the base times the height, right? Okay, look, if you forget the area of a triangle, then get the equation of the line. Right? That's not hard either, right? Who can do this? Right, remember, the final exam, we're going to be testing, right, application of integrals, differential equations. But if you got to come up with an equation of a line or something to solve one of these problems, that's obviously a reasonable expectation, right? Who could tell me the equation of this line? 2 what?
T minus 2.
2t minus 2. So definitely the intercept is negative 2. Okay, so you got that. And so the question is, what's the slope? And you said it's over 2, and it's up 4, right? So the slope is 2. That's it, right? I of t, just what he said, 2t minus 2. So you could put that equation in, and you could work the integral, right? Or you can come here and use the triangle, which is what I would do. You guys with me? Okay, so how do I get that? Half the base times the height. So we'll put 1/2. What's the base of the triangle? 1. What's the height of the triangle? Negative 2. Remember, for the purpose of calculus, areas can be negative, right? It's not like I can't have negative square feet. It just means the region bounded by the graph. If the height is negative, it's negative. Okay, and so this answer here is going to be what? Negative what? 0.5, is that right? So 1 over 0.5 is 2, times 1/2 is 1, so I just get negative 2, right? So I get negative 2 volts. Okay, and so I can come over here. We'll do the other half of it here in a minute. Okay, and we'll see what this thing looks like, right? So clearly, it's going to be below the axis. We already knew that because we knew the starting point was 0, and we knew it was a concave up parabola, right? So it had to be the case that it was below the axis, right? And so this is 0, and it's going to go down here to, what, negative 2, right? Minus 2. I'll put positive 2 just for fun. Okay, and this goes out for 6 seconds. So here's 1, 2, 3, 4, 5, 6. T over here in seconds. Okay, and so I got a starting point right here. Okay, and so we found a value right here. After 1 second, I'm down at negative 2, and it's a parabola. By the way, based on your knowledge of algebra, if you finish just what we've done so far, and you know that you just found the flat spot on the parabola, can you sketch the whole parabola? Yeah. I mean, you're done here. Right? So again, draw on all the knowledge you have, right? The point is the flat spot of the parabola, it's the vertex, it's symmetric about the flat spot. I got the left half, I can do the right half, the problem's done. Okay, and this is why this initial step of just really understanding qualitatively what you're going to do before you do the numbers, it can lower the amount of work you actually need to do the problem. Okay, so I'll go ahead and work the numbers through, but I mean, I'm done. That's the left half of the parabola is going to go through that point. The right half will finish up. Okay, but just for completeness, that means when I do the analysis, I should end up where? I should end up right here. Okay, let's double check to see if that works. So now we got to go right between, and here's the beauty of it. This statement here, between 0 and 2, these two lines apply to the entire range between 0 and 2. So the only additional step is to get a value of a point at the end, right? Because a line takes 2 points to define. A quadratic takes how many points? 3 points. Okay, so we got a starting point, we got a midpoint. If you know that's the midpoint, then you're done. But any 3 points will define a quadratic, right? Because a quadratic is ax squared plus bx plus c. There's 3 parameters in there. Okay, so I need 3 points. All right, so great. Last point will be v2. So finally, to get the endpoint, I'm going to say v2 minus v1, right, is equal to 1 over c times the integral from 1 to 2 of I of t dt. And so v2 minus v1, do I know v1? It's negative 2, so don't screw up the double negative. v2 minus negative 2, okay, is equal to 1 over c. c is still 0.5. So I got 1 over 0.5. And now I've got to evaluate this integral, which again, I've got the equation of the line if I want to find it. Okay? The equation of that line becomes more pesky if I were to do it out here somewhere. I could still do it. But on this one, it's obvious with the intercept. But still, we would probably rather just do the triangle. Okay? So over here, this integral from 1 to 2 of I of t dt is just that triangle. And so base of the triangle is how much? Right? So formula is 1/2 base times height. So it's 1/2. The base is 1. What's the height? Positive 2. So what do you get here? You get the 1/2 cancels the 2 divided by 1/2 is plus 2. Okay, so what do you have here? V minus negative 2. That's V plus 2. V plus 2 is equal to, V2 plus 2 is equal to 2. Okay? And so that means V2 is 2 minus 2, which is 0. Okay, so again, we already knew that if I have a parabola that goes through these 2 points and this is the flat spot, then the other half has to just finish it off. Okay, but what you end up getting here when you do the sawtooth, okay, is you get a periodic parabola, right, like that. Slope is 0 here. The nice thing about the numbers that we chose, okay, let me fix this. This is really not very symmetric. Okay, if I make the 2 up top look like the 2 down at the bottom, better. Okay, then what you can do is actually overlay with the numbers, right? Because this plot right here is the V of t in volts. But take a look at the numbers on the axis. These are 2's also. Okay, and so you could almost like overlay in the dotted line here. This is the current that corresponds to that voltage, right? And so as the current does this, the sawtooth current, okay, what you're getting as a result is everywhere that you have crossing the axis, you're getting the flat spot, right? So I get periodic parabolas like this. That is the result for the voltage, okay? So again, this is what we're ultimately trying to do with these sketching problems. Get to the point where we can use derivatives and integrals, understand what the slope means, about the flat spots, about the concavity, all of that. But then what do I get from the integrals? Mostly it's getting the numbers, the actual values. All right, so if you think back to the second exam, if you haven't put it out of your mind, the second exam had sketching problems, right? And one was a velocity acceleration kind of problem. The thing you'll note is on an exam 2, we're giving you numbers. We say stuff like, given this plot and knowing that the maximum position is this number and the final position is that number, okay, on a final exam, we're not going to give you any numbers. We'll give you a plot and initial conditions, right? And so that's the point. We got the numbers using the integrals. On the final, you guys will get the numbers using the integrals, okay? That's what you get. Yeah, the other thing you get is a separate way to think about the same thing. So if you're pretty sure you understand it with the slope and you're not exactly sure, then you can think about it with the integral standpoint and see if it all makes sense, right? The areas give me the same slope that I would have gotten. Okay. Questions? Concerns? Okay, so we are fresh out of material here, so I tell you what I'm going to do. I'm going to give you guys a chance to recover from your midterm activities, and I'm going to make myself available in this room for the rest of your time. This is still your time. We got a half hour. Whoever's got questions about this, about homework, about last week's homework, whatever. All right, so this is like my own little half-hour recitation. You don't get any bonus points and/or special consideration for staying for this. Okay, this is just, if you need it, I'm going to stay. If the room is empty, I'm going to leave. Okay, so it's up to you guys. All right, and differential equations next week.